Okay, so this is a course about blockchain, and today presentation is about intro to blockchain. What are the main algorithms that are used for the validation, how blockchain works, and basically what it is. So let's start with what is the difference between blockchain and the typical Web2 architecture. In the regular architecture, we have some front-end server, some front-end, and then we have servers. Usually, these servers are hosted on clouds. Example for clouds are Google Cloud, Amazon Web Services, and for example, Azure. The problem with these clouds is that they're kind of centralized, like they're controlled by a company or some entity that has full control over these servers. So if they decide, they can put some censorship on our application, or they can stop our access. They can do basically whatever they decide. So in the other case, we have blockchain, which is more democratic system. We have different nodes, machines that are connecting with each other and replicating the information in between them. And at the same time, they have some um, basically algorithm that can allow them to have some consensus. So as you can see, this is called, it is called a peer-to-peer network. It is much more resilient. It has some pros and cons, but overall, it is much more harder to put any kind of resistance of censorship here. And basically, once you deploy something, in theory, it should live forever if it's on a proper blockchain. So let's go to some definitions and basically formulations. So blockchain is a database that is shared across a network of computers. Like I mentioned, it is using this peer-to-peer architecture. So we have a network and we have a network of computers or machines that are communicating with each other. Once we record something, it is hard to change it, tamper it. Basically, it is immutable. This is how it should work. If we are using a blockchain that is decentralized enough, like Bitcoin or Ethereum or some layer 2 like Optimism, then this should be a valid property. Like it is difficult to change and almost impossible. Um, yeah, to ensure all the copies, database, basically the blockchain is making constant checks of the state of the blockchain. This is done using some cryptography tricks. And yeah, there are different use cases, and one of them is cryptocurrencies, the other is smart contracts. You can use it to have some agreement between parties that don't trust each other, or you can have some kind of currency that is fully autonomous and no one can control it, like Bitcoin, for example, or Ethereum. These are the main parts of most of the blockchains. So we have transactions, which in this case are showed as a block because it's a block of information. But yeah, let's call it transaction because otherwise it will become confusing. So we have transactions, we have blocks, which is a place where multiple transactions are stored. And then we have blockchain, which is a chain of blocks. Basically, the transactions, they are forming blocks, and multiple blocks are forming the blockchain. Um, you can see some visualization here that someone is trying to sell $100 and there is a new transaction that is created. Basically, any information that is stored on the blockchain is in the form of transaction. So once the transaction is created, it goes into the blockchain. There are multiple nodes that are validating this transaction. And if everything is correct, it is accepted in the blockchain. If the transaction is not correct, then it will be rejected. And yeah, they have the nodes have algorithm that is automatically doing that. You can see that we are adding the record here, and we have a hash. Every block has its own hash, and then we have basically other blocks that are connected to the current block. Yeah, and there are some hashes that are checked. You can see that if the hashes match, then the blocks are connected and the new block is accepted into the blockchain. If someone tries to implant a malicious transaction and try to change the state somehow, then there is a validation and the hashes won't match, and because of that the block will be rejected and it won't be included in the blockchain. And basically this is how the validation is done. And if some of the blocks isn't correct, it won't be included at all. There are two main algorithms for basically blockchain consent for blockchain to operate. One of them is proof of work, and the other one is proof of stake. So the main idea is that proof of work is using different nodes that are trying to compute unknowns, and it is using an enormous amount of computing power. So once they compute these knowns and they hash it, and if it matches some like requirements, then the miner who found the required knowns can include the new block into the blockchain, and because of that, they're receiving some reward. This is how Bitcoin works, for example. Uh, this method is kind of secure because and hard to break because it requires hardware power. So if you want to have more proof of work than the miners that are already supporting the algorithm, you have to pay a lot of funds in order to get this hardware to set up it and to start mining. And the other thing is that the hardware is limited. So even if you have a lot of money in the bank and you want to buy a lot of computing power to disrupt the algorithm of Bitcoin, you still have to wait for the delivery of this hardware. It just takes time. It's not something virtual, but you really need this hardware physically set up in your place. The other main algorithm that is used nowadays is proof of stake. Basically, the participants are staking tokens, their own funds, in order to take part in the consensus algorithm. So they are validating the blocks, and if they're acting the way they should, then they can receive rewards. But if they're trying to include malicious information or to do something which is not allowed by the network, then they could be slashed and they will lose part of their funds. Um, so these are some of the main properties of the blockchain. It is a distributed ledger. You can hear this, yeah, a lot of times during the presentation, or if you look for blockchain in the internet. So it is kind of similar term. Blockchain is distributed ledger, but blockchain is more than a distributed ledger. So it is digital, everything is on internet, it is based on some software, also some hardware, but yeah, we can say it's digital. It could be updated near real time. It really depends on the blockchain. For example, on Bitcoin, every block could take up to 10 minutes, 15 minutes, depends on the network usage. For Ethereum, it's much faster. For Optimism, is yeah, almost simultaneous. Uh, Everything is reversible and auditable. You can see the history of all the transactions, all the blocks, and like we explained earlier, it's very hard to change the historical data in the blockchain. In theory, it shouldn't be possible. Operates trustless. Yeah, you know that everything that is on the blockchain is open, it is immutable, and uh, you can trust in that source of truth without having to check it. And yeah, it is cutting the third parties. Basically, nowadays, if I want to send some dollars to you, I should use PayPal or some banking software or whatever. If I want to send you some cryptocurrency, I'm just using the blockchain, which is public infrastructure, everyone can use it, and I don't have to pay some extra taxes to in order to send you some cryptocurrency. Beside that, there are some gas fee, but yeah, we'll dive deeper into that in a while. And everything is chronological and time-stamped, so you can check which transaction have happened at what time and what was the information inside this transaction. Um, we have agreement between the nodes, which is called consensus algorithm. So basically, most of the nodes should agree that the information that is included as a next transaction is correct. So in the case of Bitcoin, you need consensus, which is more than 50% of the network. So if most of the nodes, more than 50% agree that something is correct, then it is included in the network. In the Ethereum case, it's more than 66% because it is using a different consensus mechanism. Um, yeah, as I said, the main idea is to keep the state correct and to manage the state transitions of the blockchain. There are different approaches. Yeah, like I said, proof of work, proof of stake, Byzantium fault tolerance algorithm, and they have some small differences, but the whole idea is to keep the state valid and not to lose some of the transactions or some important information. Um, Mathematical verification of messages. Yeah, if you are using the Byzantium fault tolerance algorithm, it tolerates up to 1/3 of the participants being dishonest, which means that in our case, if we have four nodes and three of them are acting correctly, and one of them is trying to be a malicious actor and to change the state in some unallowed manner, then the three nodes still have the power to invalidate the incorrect node and to basically remove it from the network. So yeah, you can imagine this at scale. So if we have 40 nodes, it is enough to have 30 nodes which are acting correctly, and they can neutralize the 10 nodes that are malicious. And in the case of Ethereum, we have thousands of nodes nowadays, and same for Bitcoin. So yeah, it is very hard for like 2/3 of the nodes to act maliciously, and they don't have the incentive to do it because from game theory point of view, miners are making more profits if they support the network and if they act according to the rules, in opposite to trying to break the rules and break the network. In that case, they can have some short-term benefits, but overall, the price of the token that is living on this network will eventually go to zero. So they will most likely lose funds rather than making some profit. Um, yeah, these are some specifics related to Bitcoin. If you want to mine the new block, you should find some hash uh, which is giving the answer to some task, or in that case, finding a hash that is uh, having enough zeros in the beginning, which is basically a brute forcing. So once you find the hash, you can broadcast it and you can win the reward that is coming from this particular block. Um, Basically, proof of work is a competition for the reward. So in the beginning, Ethereum was proof of work as well, but now it is working primarily on proof of stake. Um, so at the moment, uh, POW is supported on Bitcoin and some other chains, but Ethereum is, for example, using proof of stake. The problem with proof of work is that it is expensive for the miners to support their machines because making this computation takes a lot of computation power and they should use some GPU and Ant machines and so on. So they're spending a lot of electricity in order to have this security. Uh, yeah, it basically requires high energy, which is, according to Bitcoiners, nice because you're paying electricity bills in order to strengthen the security of the network. But in the other side, it is basically spending a lot of electricity on some algorithm that could be made more optimal. So when we have proof of stake, it is much more easier to find the answer of the task. It is not so computational heavy, so yeah, it is more greener, we can say, and it doesn't spend uh, so much computation power and therefore electricity. Uh, the idea is that if we have a proof of stake, then the block validators are randomly selected. Um, it is, of course, there is some selection. It is based on their stake, and if they are bigger stakers, therefore they have walked more funds, then they are more often selected to participate in the consensus. Of course, there are different variations, and proof of stake algorithms are continuously updated. So, yeah, maybe it will be other variations soon, and maybe there are already depending on the chain. But the idea is that if you have more tokens staked and you are the validator, you have more incentive to act honestly. Otherwise, if they swash you and if you're not an honest actor, you're about to lose a bigger part of your stake. The stake is, as I mentioned, some amount of tokens which can be measured in dollars, and yeah, you have to put some dollars ahead in because if you want to be a validator. Um, Another important thing that blockchain is heavily relating on is the hash function. I'm not sure if you're aware with that. Do you know what is a hashing function? Someone can raise a hand and explain in a few words if you're aware. Okay. Victor, do you know what is a hashing function? Окей, доста добро описание. Um, So the main idea of the hashing function is that it receives some input and at the end it returns some hex string, as Victor mentioned. So the one important property is that from the hash you cannot revert the original input. So if you want to produce the same output, you have to put exactly the same input. Uh, and these algorithms are called asymmetric cryptography algorithms because from the input you can receive the output, but you cannot do the other way around. And another important property is that no matter how big is the input, like it could be a song, a video, or a simple string, all of these inputs will result a simple hash, which is an hex string with a fixed length. Um, yeah, these are some properties of the hash function. Like it's deterministic. Every time when you input the same input argument, it will return the same hash. It is fast because the algorithm is relatively simple. And the other thing is that it is infeasible to reverse, which means that once you have the output, you cannot reverse it and receive the initial input. Very small changes in the input can result in very different outputs. We will see it in a while. So, for example, this is the hash of the word apple. You can see the result here. You cannot in any way from this hash know that the word is apple. And if we change some of the letters of apple, for example, end with F instead of E, you can see what is the resulting hash. So it's totally different. So you cannot make any connection between the output hashes and say that, oh, this initial input was some kind close to this initial input because the hashes are concretely totally different, even though the initial input is almost the same. So this is, yeah, another important property which is, yeah, very useful from security point of view. So in blockchain we have blockchain accounts. They depend on private keys, public keys, and addresses. So it varies depending on the different blockchain, but at least this is valid for Bitcoin and for Ethereum. Maybe there are difference in the bytes that are offset in the when you're building the address, but the whole idea is that the private key is some random number. Basically, you can generate it offline. So once you generate it from the private key, you can derive a public key, and the public key is basically from one public key you can have multiple addresses, and you can think of your address as your IBAN to your bank account. So you can share your address with everyone, and they can send you funds to that address, but they cannot have access to your account because they need a private key. So this is yeah, why we explain the hashing function. There is something similar here. From the private key, you can generate the address and the public key, but from the address and the public key, there is no way back to know what is the private key behind this public key and addresses. Um, yeah, so the other problem with the blockchain and also feature is that it is non-custodial and there is no central authority. So if you lose your private key for some reason, then you're losing access to your whole account. So yeah, it's very important to have a backup of your private key and to have it stored securely. The other thing is if someone is able to store your to steal your private key, then they have full access to your public key and address. So if you make a parallel with the current banking system, if someone steal my bank account or there is some problem, I can call the bank operator and tell them there is some problem with my bank. I think that there is some illicit activity. There is some problem, so can you please freeze my account and give me new access key or new password or whatever? There is no such thing in blockchain. So basically, if you lose your private key, there is no authority or place where you can go to and they can recover your private key. If someone steals your private key, they have full access to your funds. So yeah, we should be careful and we should really seriously consider the security point of view of blockchain and its implications. Um, the other thing is now you can say, okay, so if someone have my private key, they have full access to my account. And maybe this means that someone can basically brute force all the private keys and they can generate my private key by chance and have access to my account. Yeah, this is a valid concern, but basically the private key is so long, like 256 bits, that it will require a lot of computing power to compute all the possible accounts that can be generated. So if we want to make it more colorful, you can think of taking a grain of sand from one beach all over the earth. For example, it could be from some beach from US or from our beach site area or whatever, and take this small grain of sand and then go to some other place all over the world and just put it there. And yeah, basically, if someone can go and find this small grain of sand that you put it there inside other millions, billions, trillions, even more grains of sand, then basically this is the complexity, how hard it is to find this private key. Basically, the all possible variation for private keys are more than the atoms in the universe. So it's very hard. The things that protects you is that the computation is so big and intense and hard that it is not worth doing it. Like someone can try to brute force all the others, but it will take him millions of years, even with the latest software. So yeah, this is why it's so hard to hack it, and this is why you can feel very safe if you have a blockchain account when where you're storing funds. Um, this this thing that you can see here, like the diagram, is related to what is the information stored in each block of, for example, Ethereum blockchain. There is a block header. There are transactions. So, like we said, every block consists of multiple transactions. And then we have list of uncall headers. These are block hashes that haven't been included in the blockchain, but yeah, they were like to be included. So they have some valid computation and they probably could be included in some other time or yeah, basically we're storing these uncall headers because they are important for the algorithm. This is the information that is stored inside each block with more uh, basically more data that you can see here. So we have the parent hash. This is the hash of the previous block. Omar hash. I think it's important for the connection of the blocks. Beneficiary is the one who finded the who solved the task that minted that block, so he's receiving the reward from this block. We have state root, we have transaction roots. These are basically some hashing things, which I mean cryptography things that are important to maintain the state of the blockchain. We have some blocks. Here is the difficulty of the blockchain, which is written in every block. We have the block number. We have the block gas limit and gas used. Gas limit is like a unit that um, shows how much information can be stored in that block. So, for example, we can say that the gas limit is 84,000 gas units. It's a measure of computations that could be stored there. So you can think of if we make some parallel. For example, if we have a hard disk, we know that we can store on it like 10 terabytes of data. So in that manner, we have gas limit in the block. It means that we can store like 10,000 computations and mutation of the states in that block. And the gas used is the amount of computations and storage that was used in fact in practice, and the other gas limit is the maximum amount of storage that can be used. We have timestamp, which is the time when the block was minted, created. We can have some extra data, and we have nonce. This nonce is the number that I explained earlier, that the miners are trying to brute force in the case of Bitcoin. And once they find this nonce, if it's the correct one and they have the correct hash, they can mint the block. But finding this nonce is extremely difficult, and it requires terahashes of computation power. Of course, you can find it by chance, but if you want to be consistent, maybe if you're trying to participate in the blockchain with your personal computer, it will take you, I don't know, 200-300 years to find one nonce, like statistically speaking. In practice, you can find it much faster or much slower. Some of the features that are important for the blockchain is that everything is cryptography based, and you can authenticate everything, track all the transactions and blocks, and verify all the information that is there. And because of this efficiency in the verification, it also makes it scalable. So if you want to verify something that have happened like 1 year ago, you can do it very quickly with some algorithms that we'll go through in the next slides. Here it is. Basically, it is the thing that is used in Ethereum is called Merkle trees. So the whole idea is that you have transactions, and these transactions have hashes, so we don't have to if you want to verify, we don't go through all the transaction and everything that is in it, but we just check the hash of the transaction. So based on these hashes, we can create a hash that is a result of these two leaves here. And after that, we can make a hash of the two leaves that were below it. And that way we can much easily verify some information. So for example, in order to verify the master root hash, we need only these three leaves, H3, H4, H1, H2, and these two. So rather than going throughout the whole blockchain and all the things that have happened historically, we can check only these three leaves, branches, and we can verify the master root hash. We explained what is inside a block. Now we can speak about transactions. They are maybe more complex, or maybe not. They have nonce, they have gas price, gas limit. Basically, nonce is, like we discussed, nonce is some number that the miners are trying to find. We have gas price, which is the amount that you're willing to pay in order for your transaction to be included in the blockchain. This price goes to the miners that are supporting the blockchain. So in theory, it should be very low cost. For example, in the beginning, in the Ethereum was a couple of cents. At the moment, the network is heavily used and the price of Ethereum is high. So this gas price that you have to pay could be very high, and this could result in your transaction costing you like $30 to $40, which is a lot. And the same for Bitcoin, transaction cost could be $10 or $100, so it is not so efficient. But because of this problem, we have second layer solutions like Optimism. So on Optimism, one transaction could cost you like 0.001 cents. So you can still use the security of blockchain, but you can pay much less, and at the same time, it could be very fast, and the network is super scalable in general. Um, so the gas limit is the maximum amount of gas that you are willing to spend. The price is, like I said, the price that you are willing to pay, and the gas limit is the computational units that you are willing to use. Two is the address of the recipient that is going to receive this transaction value. Or if it's a smart contract, then the two address is the zero address, and you can deploy smart contracts on top of the blockchain as well. And V, R, and S are some cryptographic parameters that are part of the transaction. So how it works in practice, if you want to send a transaction, so someone requests a transaction, the transaction is broadcasted to peer-to-peer computer nodes, or in the other chains, it is broadcasted to the nodes that are supporting the blockchain. Then the nodes are verifying the transaction correctness, if everything is correct, and they can produce a valid transaction and block out of it. And if everything is fine, then we aggregate a few transactions, and when we combine these transactions, we are forming a block, and out of this block, we have like blockchain. And when our transaction is included in the blockchain, we can, for example, receive some funds. And yeah, I mean, I can send a transaction that is sending, for example, um, 10 ETH tokens to Victor, for example. And once my transaction is broadcasted, it is going to the nodes. Then they're checking the validity of the transaction, if I have this amount and so on. And if everything is correct, my transaction is included in the block and therefore in the blockchain. And then Victor can check on his phone that he has received 10 ETH coins that I have sent with my transaction. And this whole process could happen really fast depending on the blockchain. If it's Bitcoin, the result could be seen after 10 to 15 minutes. If it's Ethereum, it could take 5 to 10 seconds. If it's Optimism, it could happen in less than a second. Depends on the network consensus and yeah, how fast this processing is happening. So mm, you can see that we have discussed how we can send transactions and we can transfer value, but there are some other things that we can do on the blockchain, which is deploying smart contracts, which is similar uh, to deploying some server-side logic on centralized servers. The difference is that if we deploy a smart contract, it is decentralized. The smart contracts are autonomous, like they can do whatever is written in the code, so they cannot change that. They don't need someone to operate them. Smart contracts, like most of the transactions, historical transactions in the blockchain, are immutable. So once deployed, we know that this contract is going to behave the way it is intended because no one can change it. There is no admins or someone that can go and remove the smart contract or try to do something to change it if it's not predefined in the contract itself, but you can see it because it's open source. And the other cool thing is that if you have something deployed on the blockchain, it's like 100% of the time up. Like you can, if you deploy something on Amazon or Google, there is some chance that from time to time the service is unreliable and it goes down, or you haven't paid your billing subscription, so they can stop your service. But on the blockchain, if you deploy your smart contract once, in theory, it should live there forever and you don't have to pay any extra like funds in order to keep it up and running. Hmm, yeah, these are some of the of the important properties of the blockchain that we already mentioned, but again, scalability, like you can support thousands of transactions per second in the case of Ethereum, and for example with Optimism, uh, the energy consumption could be super optimized. So in theory, it could be less cheaper, more faster, and more scalable to have your banking system on Optimism compared to a typical backend server, because in fact the banking software require a lot of backups and strong servers and a lot of computation power. So depending on the case, it could be cheaper to host it on the blockchain because it has some built-in features that are super useful for such kind of software. Um, yeah, basically the way that they can change the information in the blockchain is only if some malicious actors are possessing more than 51% of the chain, which in the case of Bitcoin and Ethereum is hard to achieve. And with proof of stake, it requires even not only 51%, but yeah, I mean, in fact, with POS, it is not so secure because if you have more than 33% of the chain, you can try to change it. But with Bitcoin, you need more than 51%. Yeah, so you can see here more visual information about a transaction in Ethereum. So we have a timestamp, we have the sender. In that case, if I'm sending the transaction, it is my address. So you can see all the information about the transaction in the blockchain, but you cannot see who is the real identity behind it. So we can say that blockchain is semi-anonymous, which means that you have all the information and you can track the transactions, but you don't know who is standing behind this transaction. You can think of it like me going to the kiosk or the local supermarket and buying a newspaper, paying with cash. So they know that someone paid with cash and they have the cash, which is the the medium of transfer, so they can receive it and they will take it, they will have the funds, but the one who received the money doesn't really know who I was, because when I go to the local supermarket, I don't show my ID card or whatever. I just go pay with cash and then I take what I wanted to buy. So in my opinion, this is a super important property of the money itself. Of course, it could be used for some malicious activities, like you can try to money laundering or whatever. But at the same time, if everything is 100% like traceable and public, then we have another problems that someone can track all your purchases, how are you spending your money, and they can use it against you. For example, if I'm going to buy some medical stuffs because I have a condition, I don't want everyone to know what I'm buying. But if the blockchain was, I mean, if I'm paying with cryptocurrency and if it was linked with my identity, then everyone can go and historically check all my purchases that I've done for the last 10 years, which is not cool. So yeah, you can imagine if your bank account wasn't private, but everyone can go publicly to some website and check how you have spent your money and what are you buying. So it's not cool. That's why the blockchain is necessary that you have this semi anonymous thing. Like you know who is the sender, his address, but you don't know who is the sender in fact. The same for the recipient. So the recipient is the one who is receiving the funds, but we don't know who is the recipient in real life. We just know the recipient's public address, like his IBAN, and yeah, he can receive the transaction amount there. So every transaction can have an amount. And there's another argument that is data. So, for example, if I send you some funds, I can add some extra data. It could be like a memo, like I'm sending you I don't know, $10, and I'm paying for the for the dinner or something like that. Or the other thing that the data could be used could be for deploying a smart contract. And as I explained, the smart contract is a piece of code that lives on the blockchain, and it is having something like a server-side logic. Yeah, if I want to create a smart contract, basically I have to be the sender or the one who is broadcasting the transaction. It should be no recipient. The recipient should be the zero address. And inside the data, it should be the smart contract code. In the next like lectures, maybe on Friday, we will have a lecture about smart contracts, and I will show you how to deploy smart contracts on Optimism network. So you will see this in practice. And yeah, I think it's super cool to have some executable code deployed on the blockchain. Um, so after that, if you want to interact with the smart contract, the way to do it is we have only transactions, so we should use this transaction structure. So the thing that I have to do is I should send a transaction. The recipient shouldn't be a regular address, but it should be the smart contract recipient address. And I should input my parameters, or yeah, you can think of it like function parameters inside the transaction data. And that way I can call the smart contract that I've already deployed, and I can call some of its functions. So for the smart contract, we have three important steps. Like we have definition, the smart contract like code. You can think of it as a regular backend code. The contract is something like a class. The execution is when we deploy the contract on the blockchain, so we are making an instance of this class if we use this analogy. And after that, we can interact with the contract using this instance of the contract. And another important thing that is sometimes omitted, but it's in my opinion important, is auditing. So it's important when before you deploy your smart contract and go to the execution step, once you have the definitions and the smart contract code, it's important to audit it because we have seen many times uh, like bugs in smart contract that led to losing thousands of funds, and it is happening basically all the time because the sphere is relatively like innovative, cutting edge, young. It is not well established, so there are a lot of bugs that are popping up all the time. But the thing is that this is like a financial system. So if you have bugs in the financial system, you can lose like millions or billions of dollars in a couple of seconds. Having in mind that everything in blockchain is digital and happens quick. So we should be careful with the auditing step. And if we are building some project that will hold a lot of funds, then it's good to do it. And usually the audit is there are tools for automatic audit, and there are some companies that are doing audits, smart contract audits as well. Um, okay, I think that this was the the blockchain intro that I wanted to make in order to set up the stage and to make you familiar with in general what blockchain is. And in the next lecture we'll speak about optimism and layer 2s, which is again a blockchain solution, but it is kind of more scalable, faster, and built on top of the existing layer 1s. Before we continue with that, do you have any questions so far? Dure. So is everything clear or? everything is unclear and it is like too intense. Yes, go ahead. Yeah. Yes. Uh, so what is the exact question? You have a transaction? Mhm. Yes. 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 Yeah, that's a good question. So there are different like algorithms and blockchains that have different ways to handle that. But for example, Bitcoin and Ethereum, uh, blocks are minted in every, let's say, 10 seconds in the case of Ethereum, or 5 seconds, and in the case of Bitcoin, it is every 10 to 15 minutes. So no matter if we have one transaction or we have 10 or 10,000 transactions, a new block will be created every uh, like I said, for example, for Bitcoin every 15 minutes. So it is a fixed time for a new block creation. So the algorithm doesn't care if we have the whole block filled or we have only part of the block which is full with transactions. So to your question, if you have a blockchain transaction on Bitcoin and you have your transaction broadcasted, but there aren't any other transactions, if 10 to 15 minutes are past, your transaction will be definitely included in the blockchain, no matter if the whole block is full with transactions or not. Y- yeah. So, like I mentioned here, you can see that every block has gas limit. So, for example, one transaction could take, let's say, 1,000 gas units, another transaction could take 10,000 gas units, and the whole block in total could handle up to 8,000 gas units. So based on that, it is you can compute how many transactions could be included in the block, but it really depends on the size of the transaction. For example, if you are deploying a smart contract, the transaction size could be sometimes we had this problem that the transaction is so big that even this single transaction cannot be included in the block because it is the transaction gas limit is higher than the block gas limit. So sometimes you have to optimize your smart contract in order to include it in the transaction and in the block. So yeah, there is limit in the block, and it depends on the amount of I mean, some blocks can have like 100 transactions, other blocks can have only two transactions because these transactions could be related to smart contracts, therefore, they'll require more gas limit. Do you get that? Or, okay. And yeah, the more gas limit you're using, the more expensive is your transaction. So, for example, if I'm trying to send to Martin one ETH, it will cost me, there is some base limit, which is 21K uh, unit computation, or gas limit is 21K, and this is the price that I have to pay in order to send one ETH, which will result in, for example, $1. But if I want to deploy a smart contract, then it will require like I don't know, 8K gas units. So the gas limit should be 8K. Then the my transaction will cost not $1 but $4. So it is computed that way. Okay, any other questions? Okay, if we don't have other questions, I think that we can make a quick break for like 10 minutes and then we can continue with the next presentation. Um, yeah, I hope to see you here. And if you have any questions, if it's too overwhelming or too technical, please, yeah, ask me and I'll try to elaborate. It will be technical and it will be like overwhelming from time to time, but this is what it is. So yeah, please interrupt me and I'll try to explain it more clearly. So now is 6 past 10, so let's say 10:15 we can continue after 10 minutes, if it's okay for you. Okay.